Okay, so what did you get for this next one? So this one makes sense. We've got x squared plus 1. As x tends to 3, we reach 10. But what does this one look like? There's a space. So we're saying, what does it look like, by the way?
Look at this. What? That's what it looks like.
There's
That's what I just did.
on the y-axis between two and like. Oh my god! I'm very well aware.
Okay. So basically, it's actually this, isn't it? So we've got a quadratic. It looks like a quadratic, like that. Sorry about my thing. Your calculator has been quite smart, I guess. So when we're saying the limit as x tends to 0, alright, what we're looking at then is, let's pick this x value of 0. Here's the 0, the x tends to 0, and we're looking at, is there a limit as we get closer and closer to that point? So we're looking at this point here. Now you say on your calculator that that is a space.
Yeah.
Why?
Because it doesn't reach 0.
Why?
Because
It's not an asymptote. Because an asymptote is when it gets closer, like...
It's a discontinuation.
I think we talked about one like this, where can you divide through by x?
yes.
So actually this could look like x squared minus 4x plus
But it's an x.
1. Okay? That's why we have what looks like an x squared rather than x cubed. Okay? Because you divide through by x. But here's the issue, this point here. Why? Because normally your calculator wouldn't put a space, it would just put the x squared minus 4x plus 1, which is why that crossing point is what value?
The plus 1.
The plus 1. So we've got a value of plus 1 at that stage. Alright? But why is there a gap at plus 1?
Because it doesn't get to reach the point.
Why?
Because it's the limit.
There's
Why?
no value that you can put into x that will make it equal those.
No, what is the value of x as we get
0
closer to
is
0? And what do we end up with if I put 0 in?
0.
1? Well, look at if I put 0 into this one, I get 1. But what if I put 0 into the original form?
You get an error.
I get an error.
Because you can't divide by 0.
Because you can't divide by 0. So we have talked about this before. This is a fraction. So it's called a what type of function again? Rational function. Right? It does simplify to this. However, do you remember we said before about the domain of the initial function needs to apply? This we cannot have equals 0. However, as x gets closer and closer to 0, the limit of this will equal 1. So it won't actually ever equal 1, but the limit of it is 1. Because we can get infinitesimally close to 1 without actually equaling 1. Does that make sense? So that's the limit of it. Right? Make sense? Okay.
Wait, can you put that in words again? Just like you said, as something approaches.
As x approaches 0, the function approaches 1. But in this case, slightly differently to the first one, where it will equal 10, this one won't equal 1, but it's still the limit of the function. Right? Is that alright for you? Have a look at number 4 then. Let's go straight to number 4. So we've got, what's the limit, if it exists at all, as x approaches 4 of 1 over x minus 4. So what does it look like as a graph? You tell me. You draw it and
It's 1. Never mind.
draw it first. No.
Never mind. Never mind.
So I'm looking for, here's a 4. As x approaches 4, okay, either side, what happens to the y value? What y value do we approach? Put it into your calculator. Tell me what you get.
Try telling my brother that. He doesn't believe me.
Right, so, as Cassie quite rightly said, she's using knowledge from before. The one thing we do know is that x is not allowed to equal 4. But in the same way up here, look, x is not allowed to equal 0. However, there's a difference, isn't there? This one, the graph does approach 1 either side. It gets closer and closer to 1, so the limit to this sequence is 1. The limits of the function, right? As we get closer to 0. But what happens here? Now, you have just said, Cassie, that we have a what at x equals 4? An asymptote, right? So we have an asymptote there. Here's my asymptote, because we can't put x equals 4 in. We've done that, haven't we? Right? We can't put that in. Now, what about the shape of the curve then? Does it go up or does it go down?
It goes down.
Goes down. So, do we have this
Yes, pretty much.
and then this?
Yep.
Okay. Now, here's the question then. What happens as x approaches 4? What happens to the y value? Well, if we follow it, look, that's the thing, and it actually does that, doesn't it? It goes away from the other one. And as we come in from this direction, it also goes away and up to infinity. So, the question is there a limit or not? If there is, what is it?
The limit is whatever, like the smallest number less than 4. Okay.
Why? What's different about what happens here with these yellow arrows compared to what happens on this one with the yellow arrows?
Because they're going in opposite directions.
They go in the opposite direction. So as we get closer and closer to 4,
There's an infinite amount of numbers between
exactly,
that
they
and
get
that.
closer and closer to positive and negative infinity, which means they get closer to nothing. They keep getting bigger or really negative, yeah? Does that make sense? The other one above it, they both got closer and closer to 0, to 1, but they didn't get to 1, but that's the limit, they get closer and closer to 1. This other one, there is no limit to it because they, do you know the word? If they diverge, yeah? They diverge. So something like this, we have convergence. This one we have divergence. Okay, it diverges away from a particular point. There's no one particular point that we can say would be the limit to the sequence. It will just get bigger and bigger and bigger, or more and more and more negative. Is more and more and more negative smaller?
Yeah. Yes.
Yeah.
No, I heard this.
Oh, you
No,
said
it's
this
not.
like
It's-
2 weeks ago.
It depends on what you're looking
It's gonna
from.
be the same amount.
It
Because
depends
if
on
you
the.
go minus.
So I just say,
It's gonna be more negative. It's gonna be
as
bigger
x
negative.
gets closer from the right hand side to 4, so as x gets smaller towards 4, it makes sense the arrow's going up, so y gets bigger and bigger and bigger. Do I say as it goes down in the other direction, is it getting smaller and smaller and smaller?
Yes.
No, because
I
the
don't know.
negative is getting
So
bigger.
yes, I had this argument with like a 7-year-old, and I'm convinced that
Is
was
negative smaller?
Yeah.
It's the question, isn't it? There's a TOK 1 point. Is negative 10 smaller than negative 5?
Yes.
Is it smaller or is it less?
Uh,
And is there a difference between smaller and less?
yeah.
negative 10.
Less is its value. I mean,
No, negative 10 is more than negative 5 because if you have to pay $10, it's still more than 5.
How much money do I actually have though if
But
I've
negative
got...
5 is more. Wait, negative 10 is more because you
And in
get
temperature?
more.
It's more on a number scale if you're going a certain way. Depends how you're looking at it.
Yeah, so we talk constants. This is nice, isn't it? Negative is... If you go into negatives, are we going smaller? Or is smaller closer to 0? Because I would say I have less debt if I'm closer to 0.
Yeah.
I have more debt if I go negative.
Oh, you're hurting my head.
Good, I like that. Okay, do you get the idea of the limits?
I
Ish?
understand
No?
your purpose.
Pardon?
I don't get what the purpose of them are.
Okay, the purpose is what we're going to do next. So you've got to understand the limits. Limits mean as x approaches something, what happens to the y value? What happens to the value of the function? So what we're actually going to do now is we're going to talk differential calculus.
Can't you just say that x equals like infinity?
But x doesn't equal infinity. X is the one value that I've chosen. Alright? So if I changed this, by the way, if I were to maybe help you discuss it a bit, what if I said what's the limit of 1 over x to the minus 4 as x approaches minus 1?
It would be x doesn't
It's
equal
1
So I'd have
minus 5.
minus 1 over here. Here's the point. As x approaches minus 1, okay, do I now have a limit?
Minus 0.2.
So it would be 1 over minus 1 minus 4 is 1 over minus 5, which is minus 0.2. So that would be the limit of it. So do you notice how it was completely dependent on which x value I chose?
So when the bottom equals 0, like when the denominator is 0,
Yeah.
that means that there's no
So
limit.
if I'm approaching an asymptote, but it's going in the opposite directions, like one like this, there is no limit, yeah? So, for instance, what if I were to give you one like, what is the limit of e to the power of x as x approaches 10?
I don't know what he is.
It's
You
long.
is
It's
years
long.
ago, like,
Long.
okay, never mind.
Didn't they use that as like a thingy?
A thing?
Yeah, but what is the value of it? It's a
2.7.
million.
Is it on my thing?
It is on your thing, yeah.
I can't find.
What does the graph of e to the power of x look like roughly? Something like this?
It's
Yeah?
22,000.
Where does it cross?
26.
Exponential functions. 1. Now I'm saying as x approaches 10, so I'm saying 10 there. Obviously that's the point, so I'm now asking, as x approaches 10 from either side, is there a limit?
Yeah.
Yeah. And that limit would be
22.
e to the power of 10, whatever that would be. Yeah?
Wait, does that point on this side ever touch the line?
No, it's an asymptote, isn't it?
So
But if I were to write that what is the limit as x approaches infinity, right, that's correct. This is what we're going into. What about as x approaches infinity of e to the power of x?
E to the power.
And what about if we say what is the limit of e to the power of x as x approaches negative infinity? So what happens as x approaches infinity? What are we saying? We're saying that the x value goes like that on till infinity, which is never stopping, yeah? And what happens to e to the power of x as you get closer and closer to infinity?
It gets larger.
It just gets larger, so Do we say no limit?
Yeah.
Okay, keeps going up. However, what if we go in the opposite direction?
There's still no limit.
Is there not?
Oh wait.
So we're off to negative infinity.
There's still no limit.
Well, isn't it zero?
Zero, isn't it?
How?
Because it's,
Oh, because it's not.
so it gets closer and closer.
So if
It
it was,
is.
so if it was positive infinity, it'd be the opposite way around. Like if it was just, if you see.
Positive infinity, there's no limit.
So you can see what we're looking at when we talk limits. We're asking what value on the y-axis do we get closer and closer to. So if I go this direction on the x, it just keeps getting bigger and bigger. The more I go up in the x value to the positive direction, the y value just gets bigger and bigger and bigger, yeah? There's no limit to it. If I want a bigger value of e to the power of x, I just add another 1 to the x, yeah? E to the power of 2 million, how do I get bigger? E to the power of 2 million and 1. However, if I go in the negative infinity direction, if I do e to the power of minus a million, or e to the power of minus a million and 1, what am I basically getting closer and closer to? 0. So it's getting closer to the axis. It's never going to get there because it's an asymptote, but the limit to the function is 0. We're never going to go past it. The limit is 0. It doesn't keep, you know. Now if I said what would be the limit if we went to minus a million, I'd have an actual specific value. But because I say you keep going to negative infinity, it's never going to be 0. And this is the important aspect for you. It's never going to actually be 0, but the limit is 0.
Wouldn't any number in the negatives have a limit of 0 then?
No, so if I said what is the limit of e to the power of x as x approached negative 2 times 10 to the power of 100. Alright, so it's a really, really negative number. What would the limit be? Well, the limit would be e to the power of minus 2 times 10 to the power of 100. Because it would be a specific value. But because I've put infinity, negative infinity, it means it goes on forever. So it gets closer and closer to 0, but it never gets there. So it's basically saying this is the limit. That you're not. It doesn't go past this point. Okay, as x tends to negative infinity, we know because of the asymptote. So this one, it will get to that point, but this limit, it doesn't actually get to it, but it's still a limit.
Is there a formula, or you have to use like graph?
Well, you can see it's quite easy to kind of just put it in. The only thing we have to be aware of is if it diverges, or like this one here, it diverges away from that point. So yeah, we kind of need to know the behaviour of it, don't we?
Is this topic called limitations?
This is called limits. We're in, if you look at the page 4, limits and convergence, limits and derivatives.
It's at the bottom of the page.
Okay, why don't you have a look at page 197, just quickly. So, it says, maybe we could have done this before, so it says, determine whether each sequence is convergent or divergent. So we're looking for convergence or divergence. So we've got 0.3, 0.33, 0.333. Does that number, at that sequence, there is an actual sequence there, a pattern, does it get closer to something or does it move away and get bigger and bigger? What are they basically getting closer to if you keep adding a 3?
Infinity?
If you keep, well, what's 0.33333?
Well, it depends where you're trying to go to.
0.3 recurring is what?
Is 0.
As a fraction.
1/3.
1 over 3. So what's the limit of this convergent sequence? It is converging on 1/3. Yeah? 1 over 3. So it's getting closer and closer to a third. If I add another 3, I'm getting closer to a third. Yeah? I will never go past the third because you can't go past it because you can add an infinite number of 3's. Does that make sense? Tessa?
All the ones that we did with like e to the power of x are all divergence.
No. Because I said it depends what x value I'm choosing. So if I said as x approaches infinity, it goes up forever, so it diverges. But if I choose x to the minus infinity, it does something different. It converges. So what about 2, 4, 8, 16?
2, 4, 8, 6.
Does it just get bigger and bigger and bigger?
Yeah.
So it just diverges. So that's a divergent sequence. What about 1/5, 6 over 25, 31 over 125, 156? Do you think it diverges or converges?
Well, I guess if you simplify them down, so probably convergence.
Probably if you turn all those into
Decimal.
decimals. Okay. So, and what about 1 minus 1, 1 minus 1, 1 minus 1, 1
That's
minus...
the pattern.
It's just a pattern, but does it converge or does it diverge?
Both.
They're not going anywhere.
It's
It's
going
not
up, then it's going back.
It's not going.
But it's not going somewhere, it's not going, it just goes, yeah, just so we call it
So it's a wave.
divergent. It's not a wave because you don't even join the points, you just have a dot, a dot, a dot, a dot. So if you look at the answers below, so A is a convergence sequence, and as n approaches infinity, that's as you have more, we approach a third. That's what we're saying. B is divergent, so it has no limit. C is convergent on a quarter. So they get closer and closer and closer to a quarter. Right? So that's the limit as n approaches infinity. So what that means is if I've got an infinite number of terms in that sequence, it will get closer and closer to a quarter. And D, there is, as Cassie rightly said, there's no, it doesn't go anywhere, it just goes 1 minus 1. So that we would call a divergent one. Right? So what about exercise 7a? If we just have a look at it, what about 1, 3, 5, 7? Limit? No limit? Divergent. 2?
Convergent.
What's it getting closer to? What's its limit then as n approaches infinity?
3.49.
But what's that converging on?
3.5.
3.5. Yeah? Yeah? So 2, the limit would be 3.5. And in this case, it's if we were to draw the graph, it would have an asymptote, wouldn't it, at 3.5. What about 3? Convergent or divergent? 50-50. What do you notice about the plus and minuses in there?
They alternate.
They alternate. Does that mean it's not?
That means it goes like.
It's a divergent.
Well, is it divergent? Is it going somewhere?
Well, yeah.
Because it's positive and negative, but it goes above and below.
So then would it
It
be
goes
like
like
a
this.
sine graph or like a curve?
Well, it could be. You could think of a sine curve, but sine curve, what do you notice about 1/10th, 100th, 1,000th, 1/10,000th?
Multiplied by 10.
And it's getting
Big.
smaller and smaller and
So it's
smaller.
going like this.
So it's, yeah, if I thought of it as a
Oh,
sine
yeah,
wave, it would be
is.
getting smaller and smaller.
It's going to 0.
It's going to 0, yeah. So actually, it goes above and below, but it does converge on 0. Right? And number 5 is an example of the 1 minus 1, which is divergent. It doesn't come to any particular point. We didn't. I just wanted to go straight to 5. What do you think about 4 then?
Convergent.
It could be a convergent. It looks like it could be convergent. We just need to check, I guess.
I think it is.
How would you check if that was an exam
We
question?
simplify the. We find
If
what
they
the
have
decimals are.
Find a decimal. Yeah. What's the decimal for 1640 over 2187?
Yeah, it's getting bigger. Oh, getting bigger.
Is it getting bigger?
So it's a divergence.
So that was actually divergence. So don't fall for the trap that just because it's fractions, it's always getting smaller.
Yeah, it's getting bigger.
Yeah. Right, how you feeling about that one? Should we move on to that, to using it for something? Or do you want to have a bit more reading of those examples and doing some practicing?
Yeah.
We've kind of done most of the practicals anyway, just reading examples.
Wait, this spots I actually think I'm wrong. Because
Okay, let me just go through a couple of examples then to think about it. So, as someone just pointed out, if you have a sine curve,
it's convergent.
okay, it's, okay,
It is convergent.
that one we said,
Number
4.
5. I mean 4.
4.
To 0.
If we have a sine curve, is it convergent or divergent, would we say? So if I said, what is the limit as x tends to infinity of sine of x? We would say no limit. However, so this is, I think, the thing we need to talk about. This x tending to infinity, if I were to change that to be what is the limit of sine of x as x tends to, let's introduce you to 2 pi. Radians, we need to get used to using radians. It's 2 pi radians rather than degrees. Do you know how many degrees 2 pi radians is?
It's a 180?
It's not.
360?
360. 2 pi r in circumference of a circle, 2 pi is r. So I'm saying when x, so this is my x-axis, when that is 2 pi, is there now a limit or not?
X. 0.
So here it is, yeah. As we go back and forwards to that point, we will converge on 0. So do you see the difference?
And how is that a limit if they actually do move that?
Okay, so but what I'm saying is as x goes towards 2 pi. I'm not saying when x equals 2 pi.
Oh.
So we're saying as x approaches 2 pi. Now, this might make some sense to you as to why we're doing it when we talk about the next bit to do with derivatives. Okay, but can you see how, depending on what I say, x tends towards? So as x tends to infinity, I'm not giving a specific point. I'm just saying x goes on forever. All right. So there will be lots of examples like this. For instance, what about what am I talking about? What about a linear function? So I could say, is there a limit as x tends to infinity of 2x plus 3, for instance? No limit, because it just goes on forever. However, if I said, is there a limit as x tends to 5 of 2x plus 3, what would we say now?
It's 13.
It's 13. So it's not actually that difficult to find the limit, is it? It's just about understanding what happens with the graph. Right? So this would be no limit. So we're just saying, does it approach something, a particular value, or does it go on forever? So, what we want to be able to do, we are going to talk now about differential calculus again. So I don't have too long for it, but we're going to introduce it. Does anyone, well, I think you've done it before.
Yeah.
Differential calculus is for doing what?
Finding the turning point?
Okay, so finding,
No.
I'm going to say finding the gradient, because a turning point is when the gradient equals 0. Okay, so we will have all that discussion about turning points and gradients, but what I want to do with you is I want to go through the, I think it's the fundamental theorem of calculus, right? It's where it, how it was developed in the first place. You know, what did they do, right? And we need to go back to how do you find the gradient of a curve? So what we're going to do is, you know, if I give you a line, how do you find the gradient of a line, straight line? So you pick 2 points and you do rise over run. So I've got a run there, I've got a rise there. Okay, so that would be my run, that would be my rise, and I pick 2 points. What's happened to the computer? So the gradient is rise over run. Okay, now that you may have seen as y2 minus y1 over x2 minus x1, because that is just working out the change in y over the change in x. So it's pronounced dy dx, but it's actually delta y delta x. It just means a change. So you've probably seen capital deltas in physics and things, right? So you've seen dy dx. So it's just about finding the gradient. Rise over run. This is also, and we need to talk about it at some point, not now, it's a rate of change of y with respect to x. So we're saying, if I change x, at what rate does y change? And if y changes quicker, I have a steeper line. My gradient is higher. So it's a rate of change. So that's where gradient gets applied. We're doing rates of change. But we've got that, rise over run. That's not new to you. But if I said to you, here is a curve, what do you know about the gradient on that curve?
It changes.
It does change. Changes from what to what?
There's different gradients at different points.
Yeah. So, for instance, where is the gradient positive? Is it positive here?
Yeah.
Yes.
Wait, sorry.
It's positive. Tell me when to stop. It's positive until we get to...
Well, can't it also be negative at the
There.
same time?
No.
Oh wait, never mind. I'm thinking something different.
And so down here it's negative. Here it starts. Okay. So in between, it's negative. Right? So that's the negative gradient. And what do we know about the point in between? So here we have where dy dx equals 0. Okay? dy dx equals 0. So here we have a positive gradient, here is a negative gradient. Alright? Now what do we know about if a gradient goes from positive through to 0 to negative? What must it be doing? Increasing or decreasing or staying the same? So if I go from this point down here, right, and I work out the gradient, and then I go up, and the gradient is obviously changing, but it is positive, but then it gets to 0,
It's decreasing.
so it's decreasing. So we can say that the gradient up here, how far do I go before it stops decreasing? Do you know?
Before it stops decreasing. Once you hit 0.
Oh, so from 0 through to 0. But that means it goes from positive to 0 to negative back to 0, and it's still decreasing.
No.
So at some point, which should be about here, that is the maximum negative it will be. So it will be decreasing, up to that point. What happens after that point?
It starts increasing.
It must increase again because it goes from negative back to 0, back to positive. So it must be increasing at that point. Alright?
So for the decrease, it's decreasing in its positive value? Right?
So what we can say is if we were to have a number line, a scale here, right, from this value, okay, from that point there, up to that point, if we were saying that this is the gradient, here I would have, let's say, let's make up a number for gradient. Let's say it's positive 10 gradient, and at this point it's 0. This point here it is back to 0, and up here maybe it's back to positive 10. In between here it must be negative 4, let's say. So what has to have happened if this is the gradient value? What has to have happened? So from minus 10 down to minus 4, which is this bit here, it must have decreased, but then from minus 4 carrying on going back up, so it must have increased.
Wait, should it be lowest negative be like more closer to where dy dx equals 0?
But this is almost flat. So remember, think about your straight lines. How do you get a really negative gradient? A really steep negative. So think straight lines. That's positive. This line is positive as well, but more positive. If I go the other way, that's negative. That's more negative. All right. So what we're looking at is the gradient of a curve changes. It does change, and therefore, because it changes, we can't specify the gradient of the curve is always this. We want a function that can tell me what the gradient is based on what value of x I'm looking at. Does that make sense? So I want to know when x is 5, what's the gradient? Well, I might be able to work out it's negative from the graph, but what is the actual gradient at that point? And it's got to do with the x value, because obviously changing x changes the gradient. And this is what we're going to be looking at. So, what do you think would be a good way? You've probably done it before. Slow me down if I'm moving on too quickly. So if I've got this curve, let's say I want to find the gradient at this point. So I've got a value of x on the axis. What would be, how would I do the gradient? Have you got a method that you've already used before? But it's a curve. It's not a quadratic.
Body formula and differentiate.
Okay, so you already know about differentiating the function. I've not given you the function yet, so you can't differentiate it at this stage. If I did tell you the function, you could differentiate it. Do you remember how to do that? Yeah, roughly. But we're going to get to that point. Now, I need to discuss it from basic principles. So what you've had before is that you are told to draw a tangent. Do you remember that?
Oh, yeah.
So this would be a tangent to x. And the tangent has the same gradient as the curve at that point. And how do you work out the gradient of the tangent? Rise over run. So we can estimate it using a tangent. So you would pick a point and do it like that. Yeah. So you go about your point here. So that's the value you actually want the gradient for. But you draw a tangent, so you've got the same angle either side of the point. But it's estimating. So you can estimate the gradient by finding the gradient of the tangent. Okay. Now it's only an estimate. Why? So the curve isn't straight, but it's more to do with the way you have to do it. If you have to draw the so if you have to draw the tangent, then it's going to be slightly off. Your curve isn't amazing. It depends how well you can measure the points to do rise over run. You know, you can only do it to a certain level of accuracy. Let's say I can read the scale, but I can only do it to 1 decimal place, for instance. Well, what if I could do it to 5 decimal places? I'd have a different value. So the accuracy of this method is not brilliant. Okay? It's not brilliant. So that's what you could be asked to do. So, for instance, in math studies, they're still asked to draw the tangent and estimate the gradient at a point, okay, as well as having to differentiate. But this is the basic principles. Now, I know we don't have an awful lot of time, okay. So, the next thing is actually adjusting this method. We're going to adjust this method to come up with a more mathematical way. So can I get you to do a bit of reading for homework for me? Right? I would like you to look at, on page 201, there's the gradient of what's called a secant line, or a secant line. Okay, from that page, that goes through how the differentiation method works. So starting on page 201, it will then start introducing limits. Now, we are going to go through it in class, but this will run a lot smoother for you if you've done this reading first. So it's just, you know, we're just talking 201, 202. That's it. Page 201 and 202. Have a read. We are going to basically do, how did that whole stuff about multiplying by the power and reduce the power by 1, where did that come from? How did people do that before they knew that was a rule? That's what we're going to look at. So if you can have a read, and the limits thing will come into play as well.